What is it, Jamie? What was this?
We're discussing orbit types and relations.
So Dr. Sani, can you explain the whole parabolic orbit thing again?
Please.
Sure. So I think one of the things I'm going to explain again is what is an orbit, and this will be a question, potentially a question in an exam. Okay? I think this was something that Joshua asked, and it's really important that you understand what really is an orbit. So you have, I'm going to take the example of Earth. Okay. So all this is just space, right? Free space. Space around Earth. Are there orbits already there?
Yes. You said orbits already there.
Yeah.
Or you need an object.
You need an object to orbit. So there is nothing except free space here. Okay? And what happens is, so let's say you have your rocket here, right? And you launch it, okay? You go up like this and you do that. You understand? Here, somewhere here, you deploy the satellite or payload of the launch vehicle. And this starts orbiting. You got it? More often than not, this is the satellite orbiting at the position of the satellite at various time frames. Got it? It's going to keep this path unless there is resistance or some kind of force which is going to bring it down. Alright? Guys, pay attention here. I don't want you to write. Look at this first. This is a very important question because a lot of your material you are studying or trying to understand is dependent on your understanding of what an orbit is. You get this? Joshua?
Mm-hmm. Yes, sir.
I want you to stop writing, Joshua. Okay. So this, what I typically do is, this is the, what is this point? Tell me.
That's the focus.
Focus. Always. Okay. This is that focus. Now, here itself, you can get into a circular orbit, or if you push it hard, right? You can get into a elliptical orbit.
Yes.
You understand? Again, this is the, what is this? This is the focus. Yes. Typically, you don't try to break the orbit from the launch vehicle or break the gravitational pull from the from this. Okay. What you want to do is See, if you're braking, you're carrying a lot of load, right? So there's a lot of resistance here on this part. The huge fuel you're carrying is to break that resistance. The big solid rocket boosters, solid thrusters. Okay. Once you're in this, let's say you want to really brake, you can use relatively less fuel to get into different orbits farther and then break off. You get that?
So remember yesterday we were talking about we add, since we're like right now we're in the P circle, we add the square root of 2, right? It'll escape it. So is that what's just happening right there?
Now this is an orbit. I want you to understand what an orbit is.
So
Right. Here, keep in mind.
So, do we use that multiplication, that factor of square root of 2 times that velocity to actually break that? Is that what you
yes.
said? And you said no for that?
Did I say no?
Because the velocity is not higher than brake, the gravitation.
I don't. Let's trace back. Okay. Let's first understand orbit. I'll come to that. We are not always trying to break. The point is not to break away.
Right.
See, 99% of the satellites don't break away.
So what is this orbit? Like the bigger orbit? The bigger orbit?
This is a circular orbit. This is an elliptical orbit.
So how
Both of them are. You're not braking. Whatever velocity you put here in the launch. Let's say you're going to geo orbit, right? You're going to take a bigger launch vehicle up there. Okay. That time, or if you depending on what is the position and velocity. Now velocity means the magnitude and direction. If you point it like this, slightly away it's going to go. Depending on what the position of the rocket is, right? When you launch it, it's going to take different paths. You get it? What is that path or that trajectory? That's an orbit. You understand? And it will keep on following that path. That path is, what is that path? Orbit.
So
The path can be, what are the path type of paths or trajectories? You always have 4 trajectories.
elliptical, parabolic, and hyperbolic.
So you have circle, elliptical, ellipse, parabola, and hyperbola. Okay.
Those two are closed.
First 2 are closed. Circle and ellipse. You understand why they are closed?
Because they
Circle and what is closed?
You don't understand why they are closed?
because they're in a complete circle, or they connect.
This is a circle.
They return to the same spot.
This is an ellipse. This is a parabola. This is a hyperbola.
So those don't never come
Huh?
back. Those, the hyperbolic and the parabolic,
They never come back.
you just don't have it. Gone.
If they come back, it will be a closed orbit, right?
That'd be like that.
These are the closed orbits. Okay, this is the open orbit.
So what's the point of putting a satellite in an open orbit?
This is a flyby.
Okay.
This is a mistake.
Okay.
You understand?
It was supposed to be a fire.
If it is a flyby and if you don't have enough energy, you will end up in a parabola.
No mistake. Alright.
Those
You
are
get it?
used for like if you're in a slingshot, use it.
This is a slingshot.
Okay.
Okay. If you're doing a slingshot and you
Yeah.
don't do it properly,
That's a mistake.
or you could end up in, if it's better that you do a huge mistake and get stuck in that orbit than do a small orbit and get lost in space.
I don't understand like what you mean by getting lost in space. What's happening in a parabolic orbit?
So what he's saying is it's like okay. So with it doesn't return. Okay, so with that closed orbit on the he can return to his path.
Well, yeah, I got that part. Right? But
here is an example. Okay? This is your sun.
Maybe about to do an example. About to do an example.
This is your sun. Okay? This is, what is the first planet?
First planet.
Oh.
Listen to what I'm asking. Okay? This is Mercury. Mercury. What is the second planet? Venus. Then, right? Now let's say you want to get something into Mercury, right? You know where the Tesla went, the Roadster. You know Roadster is in space, orbiting space.
Yeah.
So what you do is you get into this orbit, which is this. You understand? Okay. Now if you want to get to Mercury, what you're going to do is you're going to do this.
Oh, wow.
You typically don't do it like this.
So if we don't do it like that, that's what causes something to get lost in space.
You do it like this.
So that's a parabolic orbit.
That's a hyperbolic orbit. What you do is you do this. Okay. You have enough speed to keep going and get to Mercury. If you don't have enough speed,
Oh, okay.
Question.
it's not return.
What if Mercury isn't close? Like, what if they aren't lined up?
Huh?
You know, you have them lined up a certain way. What if the planets aren't lined up like that?
They are not lined up. So that is the reason the timing of the maneuver is you cannot go to Mars anytime you want.
Yeah.
Right? So when you think about going to Mars, you go to Mars only when it is closest.
Okay.
You time your maneuver such that it's closest.
So that's
Yeah, you have to time your
that's
maneuver. It's not lined. Yeah, it's not. Because it very rarely lines up.
So
How long takes a long time. Like a long time. That's why no, I'm being serious. Like that's why
It takes a long time to just if you understand.
that's why the time between missions takes so long, just because
Right.
Yeah.
It's not about lining up. It's about what's practical to. You don't always do it when they line up, but you try to do it when it makes sense.
Yeah.
You know, you say, okay, this is the closest approach. Let's say if it is going to line in 20 years, you're not going to wait 20 years, right? Then you won't be able to launch something credible.
why don't you just go straight there?
You got enough fuel?
That is what you should not say as a aerospace. And that's what I'm trying to teach you. It's like what happened to Columbia and what happened to Challenger?
They explode.
They tried to go straight. And they did not do it intentionally. You burn. You just destroy yourself if you try to go straight. Okay, don't say that. If you say that, then that is what I'm trying to teach you. What are the orbit types? Did we discuss a straight line?
Yeah.
With a parabolic or a flyby, are
You'll burn yourself essentially. If you try to go straight, you'll use up too much fuel and you won't be able to. You think about watch these movies of building the space shuttle was actually a big disaster, so to say. Okay, because you never fly something with wings. What is that? Something which has wings. It has a lot of surface area. And a lot of surface area means managing that is going to be very difficult. That surface area has to be parallel to the atmosphere. If it is perpendicular, it has to be really, really strong to resist that burden. Okay. Look at the asbestos or the ceramic tiles on the space shuttle. How much they spent every time the space shuttle came back just to make it ready again for another mission, $2 billion was spent. Billions of dollars were spent every time the space shuttle came in. Just, you could get a new module, a new capsule in that money. What is the newest vehicle which is being readied for something like this? How do we get to space shuttle now?
Russia.
Russia, right? We depend on what is the Soyuz capsule. So now we are going to USS developing. So look up this Orion capsule. Okay. Boeing has developed something. NASA is developing the SLS, the Space Launch System, with the Orion capsule. So that capsule is like a rocket. It's like this, so that there is very little resistance. So it will come like this. It's the path of least resistance. You're not going to use air, so you don't. That's the reason you don't go straight. Okay.
But can you say why you don't go straight? Well, I mean, I understand that.
See, what is happening is gravity is pulling, right? Your velocity, if you're doing that.
I mean, I guess what I'm asking, what straight are you talking about? What dimension are you talking about right now? Like, it's straight.
Straight in the sense, if you're going from this to this. If you're going to Earth and Moon, right, you don't go like this.
So you're saying you can't travel in a straight line?
You cannot. You can travel in a straight line with an infinite amount of energy and infinite something which is not going to unobtainium, rocket made of unobtainium, infinite fuel. Huh?
You say that there's a possibility that traveling in a straight line, or just not?
You just don't try. Unless you understand it, it's a disaster in the making. Okay? If you think about, you want to do this.
Too much.
You get it? Even when you're coming into Earth, right? From anywhere in orbit, you don't do this. You understand? You do. You spiral in. You'll essentially the resistance which is you're going to face when you're doing that will burn you up.
Oh, okay.
Heat, and imagine what is the acceleration here. It's 9.81 meters per second. So it'll eventually you won't be able to control that. It's a huge technical problem to solve if you're going to do it straight. Yes.
I'm glad you drew that because that's a question I had. You know how when you come into Earth's orbit, you spiral around. So the moon that orbits us, what keeps it from doing that?
There is no. So moon is also, as long as, how do you spiral in?
You spiral in.
You have to use. See, you have to understand the conservation of momentum. Okay?
Yeah.
So this, what keeps the moon like that? It's the conservation of momentum. Okay.
Okay.
How can you change momentum? You need external force.
Yeah.
This atmosphere gives you that external force.
Okay.
So the space shuttle, or let's say the space station, is actually doing that, but it is constantly being pushed away because it is in the lower atmosphere where there is atmospheric resistance. Where moon is, there is practically no resistance at all. So it just keeps on doing that. Although there is, and plus the mass of the moon is really, really large. So after millions of years, it would have come a little bit closer. Okay?
So, Dr. Shundi, with the hyperbolic.
Yeah, let's talk about the breakaway, the formula. Okay.
Right. I just have a quick question, right? So when we do the flyby, are we not expecting to get the craft back, the satellite back? Are we not expecting to get it
You
back?
only do flyby to get to another place. You don't do a flyby. You cannot do a flyby in Earth you have to go to another planet.
Right.
You have to have an infinite amount of energy, not infinite, but a lot of fuel. So when we went to moon, we did not carry a lot of fuel, right?
Right.
To get out of there. We did carry a lot of fuel, but imagine if we did that with Mars. We have to carry a lot of fuel if we go to Mars to get out of there. You know why?
The gravitational pull is strong.
Gravity is not. Moon has no atmosphere.
Dr. Sunny, can you repeat the question?
When we went to moon, we did not carry a whole lot of fuel to get out of it. You have seen those ads, or you've seen those memes where if somebody pushes you off the moon, you'll actually go flying. You haven't seen that?
Yes, so the gravitational pull on the moon is more or less.
Not gravitational. There's no atmosphere.
Okay.
Wait, so you have to have an atmosphere to have gravity.
You could, if there was no atmosphere around Earth, you could float even on the surface, just inches above the surface. You could orbit.
So so
Huh?
that'd be pretty cool.
If there was no atmosphere. You understand? Because there is no resistance.
Even with gravity still being present.
Yeah.
So there's no resistance.
So once you start moving there, right? Once you give that velocity, understand this. If you set something at a particular speed, according to physics, it will keep that speed. You understand? Unless there is resistance. Friction. Why do you slow down when you're going on road? Friction. The fuel you need is not to keep the speed, it is to overcome the friction. The friction, the fan, once you set the fan to rotating, what is the electricity used for? To overcome the resistance. The fan will do that if there was no resistance. You understand?
Yeah.
So if you have Earth, if you set something like this, it will keep on doing that if there is no resistance.
So on the moon, let's keep going.
Yeah, because there is no atmosphere around.
So it only take a little bit of fuel.
A little bit of fuel to get out of it. But if you're going to do that on Mars, you need to carry as much of fuel as you need for.
Alright.
Okay. Now, we talked about, again, just a reminder, E is equal to 0 and epsilon is less than 0. Circle. E ellipse, okay? E equal to 1 and epsilon equal to 0. Alright? Always keep this in mind. So you have, if you look at this Vy equation, epsilon is equal to v square over 2 minus mu over r, right? For a parabolic orbit, epsilon is 0. Alright, so this V parabolic is nothing but V escape. It's the velocity required to escape. Okay? And if I equate this, you're going to get root 2 mu over r. Alright, this is V circle. Okay, so that is how you write root 2 V circle. And what this says is, if you are in a circular orbit, if you increase the velocity by 41% or 1.41 or square root of 2, you're going to escape that particular orbit. This is true for any orbit. Moon, Earth, Sun, right? So elliptical orbits, I think we have talked about this. Let's look at this quickly. Okay. I'm not going to derive this. But what I want you to, in the formula sheet, you can have this formula. Okay? I want you to be able to apply this formula. This is an indication of what eccentricity is. Okay. So here, what is this point? P, this is the P direction. This is focus. This is the unoccupied focus. So here typically what happens is your Earth will be like this. Okay. The center of the central body is the focus. Alright? The orbiting body is here. What is this? R. What is this? Theta. This is center. This point. What is this distance? A, semi-major axis. What is this distance? Semi-minor axis, or B. Okay. Here, I need you to remember this formula. A you can prove this, in fact. What is RA? What did we say RA is? You can, of course,
This is a vector of
these two are very important formulas. You can,
Say RA is
what did we derive RA as? A square over mu
over 1 minus b.
right? Okay. And 2a is what? Or RP is a square over mu divided by 1 plus a. Get it? 2a is what? RA plus RP. You with me? This is RA. Sorry, this is RP. Right? And this is RA. You get it? So 2A is RA plus RP. Right? This half of RA plus RP is A. RA plus RP is 2A. Essentially, this is the two words for this. Huh? Circumference is that. Two words for this.
Oh, it's the A word.
Major axis.
Major axis. A is apoapsis. This point A. But A is, so you have to always distinguish this capital A, capital E. These are points. This is distance. Okay? And if I substitute these two here, you're going to get h square over mu. Okay? One over 1 minus E plus 1 over 1 plus E. And if I simplify this, I'm going to get h square over mu. 1 plus E plus 1 minus E divided by 1 minus E. Alright?
Dr. Sunny, can you explain equation 2a? I'm just confused because RA and A are two different distances.
Yeah. This is 2a. Alright, pay attention here, okay? Just a minute. Give me a minute of yours. Stop writing. This is 2a. You agree?
Yes.
This is?
RP.
This is?
Alright.
So RA plus RP is 2a, right? That's what it is.
Well, I mean, I get that, but I just don't. What I'm confused on is why RA and A at the bottom from the center to the apoapsis. Why is that a different distance than RA? Do you want to show you?
Oh.
Yeah.
RA is from the focus. It is different. Why do you mean it is different? Half of 2a is A.
Yeah.
A is measured from the center.
Okay, so it's
RA and RP are measured from the focus.
Okay. Wow, that makes sense.
Okay. So here, if you look at this, you simplify that, you have 2a is equal to 2 divided by, sorry, h square over mu 2 divided by 1 minus e square. Okay? And if I cancel this, a will be A square over mu. You may be asked to prove this. You can write down this formula in your formula sheet. You can write this formula. You can write this formula. You can even write this formula, but you need to know how to prove this, how to get from here to here, or even here to here. Okay? Now, I need you to note down this formula. So I won't prove this.
Hey, Doctor, what does that mean? With the last formula that you wrote?
It's an expression for A, semi-major axis.
Is A supposed to be H squared over mu? Mu to whatever it
Is
is.
H square over mu. So if you start from here, this you know, right? This is the orbit equation.
I
Okay?
understand. I'm just asking, like, is it multiplied? Is it
Multiply, yeah.
into fractions?
Multiply this by this.
Okay.
This multiplied by this.
Just like it's a sign.
We don't use that multiplication sign because that means cross in this context. Okay. What does this relationship tell you? What does this relationship give you? I think we have talked about this quite a bit. You have E square is equal to 1 minus E square over A square, or E is equal to 1 minus B square over A square. I'll leave it here. Does this make sense?
Where did that come? Oh, is that coming from that equation?
Mm-hmm.
Okay.
So it's B over A, right? If I remove the square root, it will be B square over A square. Okay? And if you take the E on the other side, then you'll get this. What does this relationship tell you? Yes, yes.
So that means that
E square. Does this answer something for you?
Yes.
What does it answer?
You said that A is equal to B, so that'd be 1 minus 1, which is 0, and B is equal to 0. Right? For our circle.
You've been asking me what eccentricity is, right? It is this. So for a circle, what do you know about A and B? Same, right? So it's E is equal to 1 minus 1, 0, right? You get it? What do you know about ellipse? A is always greater than B. So this will never be greater than 1. You get it?
How did you come up with that formula for zeta?
We can derive that. We can derive that. Yeah, we can derive that from geometry.
Okay.
Okay. So, but this, do you get this? No?
So it'll never be greater than 1, so it'll be less than 1.
It will be less than 1. So 1 minus less than 1 is?
Oh yeah, okay.
A is the semi-major axis. Semi-major axis. So semi-major axis is always bigger than the semi-minor axis, right?
How could it be that if B and A are equal? Oh, because it could be a
Certain.
Yeah, I'm sure.
For parabola, what is A?
0.
Right.
What is it?
Is
Infinity.
Oh.
Something over infinity is?
0.
1 minus 0 is?
1.
1. For hyperbola, A is actually.
I thought 2A would be infinity.
Huh?
I thought 2A would be infinity, but not A, because A is like missing from the center to
Yeah, it is center from, it is the distance from A to, if A is infinity, 2A is what? Infinity. If 2A is infinity, what is A? Infinity divided by some number is infinity. Infinity multiplied by some number. Infinity. Infinity over infinity. Not defined.
Alright.
But anything divided by 7 is 1, right? So anything divided by 7 is 1, right?
Yeah, but it can be any number.
It is not a number. It's,
Well, I'd say number 13.
so understand this. Okay? And couple of other formulas. Okay? You can note this down.
I have a question.
Yes.
Does formula have a center?
Does it have a center?
Yeah, that's not right.
Huh? Does it have a center?
You can't have a center if it's not open, right?
Huh?
You can't have a center if it's open, right?
I'm asking you, can it have a center?
You can't have a center if it's open. It can be now. Because if it's open, you don't know how far it's open.
yeah, that's it.
I say no, just because you don't know how far it's open. If it's open, the parabola is like it is like that. And it goes to infinity.
There's no center.
It's like easier.
If there is center, then there is E.
Yeah,
A is finite.
That's
That's what I know you are getting to that. So if there is center, then there is definite A. Right? If there is no definite A, then there is no center.
I mean, but even though it's like falling in order of path, like, just because it doesn't complete the shape doesn't mean that it doesn't have center.
Forget about the orbit. A parabola as a geometric shape does not have a center. What? So that's the reason I keep stressing the word focus. You understand? The focus is important. The central body is at the focus. You don't know where the other focus is. You don't know where the center is. So you don't know. If you knew where the center is, your semi-major axis would be finite. Okay. Now I need you to know this formula as well. And the last formula is, of course, this one.
Which orbit is this for?
Hmm?
Is this for a specific orbit? Or?
That's a good question. Let me answer that. Just give me a second. This will be given for derivation. These two, I won't ask you for derivation. This is very simple. Again, just if I ask you to show me that this can be represented like this. Okay. How would you go about doing that?
What's the question again?
I say prove that E can be represented like this. How do you go about doing that? You just substitute h square over mu 1 minus E minus h square over mu 1 plus E, right? Divided by again h square over mu 1 minus E plus h square over mu 1 plus E.
One of those should be a plus.
Huh?
Should be a plus, right?
So if you simplify this goes. Okay. So you're going to get 1 minus E minus 1 plus E. You get it? Last. Sorry, this would be plus 1 divided by 1 minus E minus. Alright, I'll let you do this. Do the simplification. Okay. So to answer your question, this is all generic. Okay. What is this formula? Time period. This is Kepler's third law.
Which this equation that you just put up, this, another one before it, another one after it. Yes, sir. So, how did you, what are you trying to do exactly? Sorry? Yeah, this is.
Show that.
Are you trying to make this go from here to here, or from here to here?
So we have to substitute this. You start with E equal to this,
Okay.
and then
You plug.
you show that E is equal to E. You show that all this reduces to E. You make it
So that all reduces to E?
E reduces to E.
Like just regular E?
Yeah.
So you're trying to show that E equals E?
Yeah.
Okay.